Hello, everybody. Welcome. Thank you so much for joining us today. For those of you who don't know me, my name is Chris Taylor. I'm Vice President and General Manager for Crane's Global Polymer Group, which includes our brand Rubber News, and I will be your host today. Today's webinar is From Rubber to Environment, Detecting 6-ppd and 6-ppdq, and it's brought to you by Frontier Lab and Shimadzu Scientific Instruments. We're delighted to have a whole panel of experts with us today. And here's what we're going to dig into today. As concern grows over tire-derived chemicals in the environment, labs need fast, reliable ways to detect them. And our presenters today are going to introduce a microfurnace pyrolysis method for detecting 6-ppd and 6-ppdq directly in tires and recycled rubber, and doing so with minimal sample prep. So using standards and real-world samples, they're going to show us how selective ion monitoring and mass spectral interpretation make for confident compound identification, and they're going to be straight with you about both the strengths and the limits of this technique. So I'm really excited to be joined today by a whole panel of folks who know this work inside and out. I'm going to introduce them to you really quickly. Heather Juzwa is Senior Field Sales Engineer at Shimadzu. Rogine Belganet is Technical Director at Frontier Lab Americas. Mark Waxmonsky is Technical Support Manager for Mid-Atlantic for Shimadzu. And Dr. Peter Tandler, Professor of Chemistry of the Center for Science Excellence. Quick housekeeping note before I hand this over and we get started. You can ask a question at any point during the webinar. You'll see on your screen there's a Q&A box. Just drop your question in that box as you think of it, and it'll send it our way. We'll have a dedicated Q&A session at the end, and we'll get to as many questions as we can. But again, you don't need to wait till the end to send in your question. You can put it in that Q&A box, and it comes straight to us. With that, let me hand it over to get us started to Heather. Heather, the floor is all yours.
Thank you so much, Chris, and welcome, everybody. We're delighted to be here today. Since our founding in 1875, Shimadzu has maintained a deep and enduring commitment to academia, recognizing that scientific discovery begins in the lab. From our earliest days supplying precision instruments to educational institutions in Japan, we've positioned ourselves as not just a manufacturer, but a true partner in learning and innovation. Over 150 years, this philosophy has remained constant. Empower researchers, educators, and students with reliable, high-quality instruments to enable breakthrough discoveries. Our instruments have supported countless academic milestones, advancing research in chemistry, life sciences, environmental, and beyond. One way we support academia is through our SPARK grant program. This grant is individualized to a specific set of goals for the institution we select, but are based on shared vision and values. If you look at the schools we've selected, they represent a diverse range of regions and educational environments, but they share a common focus on fostering curiosity, critical thinking, and practical application of scientific concepts. Through the recognition of the SPARK program, we aim to support and highlight schools that are shaping the next generation of scientists. In 2019, Shimadzu selected Walsh University as a partner because Walsh provides its students with higher education that fosters critical thinking, effective communication, and personal and professional development. It's clear that Walsh is dedicated to educating its students to solve complex real-world problems and become the next leaders in the lab. Since 1991, Shimadzu has been working with Frontier Labs, coupling their microfurnace pyrolysis onto our gas chromatograph mass spectrometers. And when we formed the partnership with Walsh, a beautiful marriage was formed, and that brought us the collaboration that brings us here today. We coupled Frontier's pyrolyzer on Walsh's GCMS QP 2020 NX, and since then we've used it for a variety of different projects, from microplastics in the environment to automotive, and with their location in North Canton, Ohio, a stone's throw from the rubber capital of the world, Akron, of course, rubber. And speaking of rubber, 6-ppd is what brings us here today. It was discovered in the 60s, and by the 1970s, it was used ubiquitously everywhere. And there's good reason for that. It's very inexpensive. It works well in dynamic moving systems. It resists flex fatigue. It's shown to migrate to the surface to prevent cracking, and it works in natural and synthetic rubbers. So you see it in different areas. On the consumer side, it's in the soles of shoes. And on the industrial side, it's in conveyor belts and hoses. But it's believed that the largest application of these and the largest deployment of 6-ppd is in tires. And so it went for 50 years. Then we hit a roadblock. In 2020, a group from the University of Washington published in Science that there was a compound in tires that was causing acute salmon mortality. And the mechanism for this isn't known, but what happens is the salmon are seen gasping for breath on the surface of the water and twisting around. And this was reported as early as 1999 by citizen scientists. And as you might imagine, it is felt the most strongly in the Pacific Northwest because that's where we have the highest salmon population. The paper went on to say that the places that are most effective were creeks that were near heavily traveled highways, and things got worse whenever there was a heavy rain followed by a dry period. So that pointed to stormwater runoff as being the issue. But there are hundreds, thousands of compounds in stormwater runoff at varying concentrations, but they targeted the issue to be with 6-ppdq. And 6-ppdq is formed via oxidation of 6-ppd. So the tires are going along the highway, they're flaking off these pieces of 6-ppdq or ppd, and then it's becoming 6-ppdq and killing the salmon. How are we analyzing it? We know the problem now. Most people are using liquid chromatography tandem mass spec triple quad LCMS. There's even an EPA method for it, 1634. It is incredibly sensitive. Our flagship LCMS 8060RX can see 0.002 part per trillion of the compound, and it's incredibly selective. But it's not all sunshine and roses. LCMS triple quads are a very expensive investment. We're talking $350,000 to $500,000 to purchase it. You have to do sample prep. You can't just introduce the tire into the instrument. So you've got to do solvent extraction, solid phase extractions. And LCMS is a soft ionization technique. So I'm protonating or deprotonating my compound of interest. So it's helpful. No, Shimadzu can train anybody, but it's helpful if you have people in the lab who have a little bit more expertise, because what you're going to get is a peak and a number, a mass to charge number. There's no commercial libraries to help you identify the compounds of interest. So we're proposing today analysis via GCMS. And this is nice because a lot of rubber labs already have GCMS capabilities. It's way less expensive to add a pyrolyzer onto an existing technology than it is to invest in something completely new. And unlike LCMS, GCMS is hard ionization. We're hitting the compound 70 electron volts. They'll reliably fragment the same way. And so we can use commercial Wiley and F-Search libraries from Frontier. And it needs next to no sample prep to be able to get results quickly. With that, I am pleased to turn things over to Rogine to start the rest of the webinar.
Perfect. Thank you, Heather, for the great introduction, and also thank you everyone for joining us today. So today's webinar is actually organized into 3 parts. I'll begin with a brief introduction of the microfurnace pyrolysis GCMS, and then I'll talk about the workflow of the different modes of operation that makes this technique useful for material characterization. I'll then walk through a rubber application example showing how this workflow can be applied for the identification and quantification of 6-ppd. And then following that, Dr. Peter Tandler from Walsh University will present his research on applying microfurnace pyrolysis GCMS to rubber samples, including his work on 6-ppd and also 6-ppdq. And then lastly, we'll conclude with a live Q&A session. Okay, so let's start with the system configuration of pyrolysis GCMS for material characterization. The microfurnace pyrolyzer in this figure is shown as the component number 2. and it functions as a programmable temperature-controlled inlet that connects directly to the GC injection port. So one important aspect of this design is that there is no transfer line between the pyrolyzer and your GC. And because the sample travels directly into the GC column, active surfaces and any cold spots are not there. The system can be configured with several optional accessories as well, and that depends on the analytical objectives that you have. For example, the AutoShot sampler automates the sequential analysis up to 48 samples, and that's shown as number 1 in this figure. Or the microjet cryo trap can be used to trap and focus highly volatile compounds. So if you're doing any quantification or identification of reactive monomers, for example, you want to use the microjet cryo trap. The selective sampler is another accessory that enables hard cutting analysis, and I'll talk about that shortly. But instead of analyzing the entire sample, with the selective sampler, it actually allows you to analyze only the portion you're interested in. You can also see the vent-free GC-MS adapter shown as number 6 in this figure, and that allows the column changes without venting your MS. So we'll see when you do EGA, which is a thermal analysis, versus, for example, flash pyrolysis, which is a separation analysis, you might have to switch the EGA tube to a separation column, and you could use the vent-free GC-MS adapter to do it without venting your MS. And then finally, the F-Surge interpretation libraries that provide automated interpretation of polymer and additive data generated during the analysis. So now I would like to discuss several analytical characteristics of the microfurnace design that are really important from a scientific perspective. So the first is the temperature control. In pyrolysis, temperature really directly influences the products that are generated. And small differences in heating conditions can actually produce different pyrograms, and it can affect the quantitative analysis. So with the microfurnace design, the sample is heated uniformly inside a temperature-controlled furnace rather than by direct contact with a filament or a carrier point foil. And this really provides a very precise temperature control. And then the second advantage is the inertness. So all sample contact surfaces are quartz or deactivated surfaces, which eliminate any secondary reactions or adsorption or contamination. And also the operating principle is another important factor that sets the microfurnace apart from the other technologies in the market. So in this case, with microfurnace, the sample actually remains at an ambient temperature inside your sampling cup while the furnace is preheated to that desired temperature set. And only after the furnace reaches the programmed temperature is then the sample introduced into the furnace. So this means that the sample is not getting exposed to any gradual heating or evaporation or saturation before the analysis starts, which actually that eliminates premature evaporation, degradation of any volatile compounds prior to the analysis. And then all the generated compounds or the pyrolyzate, they get continuously deposited on the GC column for separation, and then in this case, they go to the MS for the identification. So another strength of the microfurnace platform is that it supports several different analytical modes using the same instrument. So it is one platform of microfurnace Pyrolysis-GC, but you can actually perform multiple analytical techniques using the same platform. And these modes include evolved gas analysis, known as EGA. You can also perform thermal desorption or flash pyrolysis, which is also known as single shot, a double shot analysis, or a hard cut or thermal slicing. And each mode really answers a different analytical question. And today I'll go over each mode and show example of each one. So to simplify material characterization, we actually developed what we call the method map. And the idea is very straightforward, especially for unknown samples. Rather than guessing the pyrolysis temperature, we first obtain thermal information about the sample. So the first step is evolved gas analysis, or EGA mode of operation, which really provides a clear picture of the sample's thermal profile and showing when different compounds being evolving during the heating process. So EGA-MS provides chemical information about the evolved gases. And once the thermal profile is obtained from your EGA thermogram, we can then define the temperature regions of interest and then choose the most appropriate analytical mode, whether you can do a thermal desorption or flash pyrolysis or hard cutting, or maybe even a combination of these techniques. So in summary, EGA is the first step, and it really guides you on what to do next. Now, this is a slide we are showing about the EGA experiment. A short and deactivated tube is placed into the GC oven. So this is not a separation analysis. This is a thermal analysis. Well, you have an EGA tube inside the GC oven. And then the sample is introduced into the furnace, which is then programmed through a controlled temperature ramp. For example, in this example, we did the temperature programming from 40 to 600 C, 20 degrees per minute. And then as compounds evolve continuously from the sample, they travel directly to the mass spectrometer from your EGA tube without any chromatographic separation. And then the result is a thermogram showing the detector response, which in this case is your MS, as a function temperature and a retention time. And this provides a rapid overview of a sample composition and a thermal behavior of your sample. So once the optimum pyrolysis temperature has been established from EGA, flash pyrolysis can then be performed. This is one of the modes of operation. Either it's flash pyrolysis, or you could also call it a single shot GCMS. And in this example, the selected temperature is 550 degrees Celsius. And that's the temperature we obtained from the EGA thermogram. The sample then undergoes rapid isothermal pyrolysis, generating decomposition products that are separated by GC and then, of course, identified by MS in this case. So the resulting pyrogram, as you can see in this figure, contains information from both the polymer decomposition products and also any additive or contamination that you have, because you're obtaining one pyrogram that has all the feature of the sample in that one pyrogram. And then using your F-Search libraries, as I mentioned, you could do some pyrogram analysis, or you could do peak-by-peak analysis for the pyrolysate of a polymer. However, many real-world samples, as you guys know, are more complex, and they contain both volatile additives and even mixture of polymeric compounds. So a double-shot analysis, as you can see here, actually separates these into two analytical steps. The first step is the thermal desorption, where any additives, any residual solvents, antioxidant, plasticizers, or other volatile compounds are released without decomposing the polymer. Basically, you're using heat to extract the additives from the heavier polymeric portion of your sample first. And then the second step performs flash pyrolysis on the remaining polymeric portion of the sample. So this is one sample to analysis in this case. And instead of combining everything into a single complex pyrogram, then you can obtain two complementary data sets, one describing the additives and volatile portion of the sample, and then one describing the polymeric portion and the heavier parts of your sample. And then hard cutting or thermal slicing really extends this concept even further. So instead of separating the sample into only two fractions, as we just saw with the double shot, which was thermal desorption followed by flash pyrolysis, with hard cutting, the thermal profile can then be divided into multiple temperature zones, and you obtain multiple GCMS chromatogram for each of the zones that you identified from your EGA-MS. So then each region is analyzed independently, and then this can provide a much greater resolution when studying highly complex formulation, degradation processes, or unknown sample. And a lot of our customers, they use it for reverse engineering and deformulation of their competitive type samples as well. So now that we've discussed the analytical modes, the method map, for example, EGA, single shot, double shot, hard cut, now let's look at how this workflow can actually be applied to a rubber sample. And the objective of this work is to identify the polymer composition of a tire rubber while also quantify the antioxidant 6-ppd. So another advantage of Pyrolysis-GC, as Heather mentioned, is the simplicity of the sample preparation. So in this case, we just used the tire rubber. It was analyzed directly as is. A very small piece of rubber was simply cut from the sample and then placed into the cup, and no solvent extraction, digestion, or other pretreatment was required. And then for the quantitative analysis, we use the matrix match calibration standard. So first, a 6-ppd standard solution was prepared in toluene, and then known amounts of this standard were then combined with the SBR solution, which was closely matched with the polymeric matrix of the the sample. And then by preparing the calibration standards in a similar matrix, both the standard and the unknown samples present comparable thermal desorption kind of compatibility to each other. So as we learned, following the method map, we first used evolved gas analysis, or EGA, for the sample. About 0.2 milligrams of the tire rubber were analyzed while we programmed the furnace from 80 to 700 degrees Celsius, 20 degrees per minute. And then the EGA thermogram provides two important pieces of information, and you can see the thermogram here on the screen. So first, it told us about the thermal regions where compounds evolved from the sample. So you can see the shoulder at the beginning at the lower temperature zone, where it actually corresponds to the volatiles and the additive portion, whereas the more intense peak, which is coming at a higher temperature, that's for the polymeric portion of the sample. So using the F-Surge EGA library, the higher temperature region was identified as a styrene butadiene rubber, or SBR, and you can see a screenshot of the F-Surge interpretation libraries here. And then more importantly, the EGA thermogram gave us the temperature window, the appropriate thermal desorption temperature where the additives evolve before the polymer decomposes. So based on this information, the thermal desorption range was set from 60 to 370 degrees Celsius for the next analysis on the sample. So here you can see the thermal desorption GCMS of the tire sample, which shows the volatile and then the semi-volatile additives of the sample while the polymer matrix remains intact. So we only extracted the additive portion from the sample. And 6-ppd was identified and then quantified using the previously prepared calibration standard. So once 6-ppd had been identified, the next step was then selecting the appropriate ions for quantitative analysis. This figure here shows both the total ion chromatogram, the TIC, and also extracted ion chromatograms, EIC, for a 1000 nanogram calibration standard. And the ion at M/Z 211, as you can see, was selected as the quantifier ion because it provided strong signal intensity without any interference from the SPR. And then the ion 268 was used as a reference ion to confirm the compound identity. Using the selected quantifier ion, then the calibration standards containing 0, 50, 250, 500, and 1000 nanograms of 6-ppd were analyzed. So we did a 5-point calibration curve. And the resulting calibration curve demonstrated excellent linearity, as you can see here, with an R-squared value greater than 0.999. And this indicates a highly linear analytical response across the concentration range and provide actually confidence in the quantification analysis. And finally, the developed calibration curve was applied to the tire sample. And using the external calibration curve that we just created, the concentration of 6-ppd was identified to be around 1200 milligrams per kilograms. So to summarize the workflow, first, the sample preparation was extremely simple. The rubber sample was analyzed directly after cutting a small piece, placing it into the sample cup. So typically with Pyrolysis-GC, you can eliminate any solvent extraction or sample preparation because you're using heat as the main factor to be able to thermally extract those additives and plasticizers from your sample. And second, multiple analytical techniques were performed using the same microfurnace pyrolysis GCMS platform. And we begin with EGA-MS to understand the thermal profile, and then we perform thermal desorption and then flash pyrolysis on the sample. Also, another advantage is the comprehensive characterization. So as you saw, using the F-Search interpretation libraries, we could also identify the polymer as SPR and then any additive in your sample. I would like to also acknowledge everyone who contributed to this work, and then the references are listed here for anyone interested in additional information. And with that, I would now like to transition from the analytical methodology to a real research application. And it is truly my pleasure to introduce Dr. Peter Tandler from Walsh. Peter has been applying microfurnace pyrolysis GCMS to rubber samples, including studies involving 6-ppd and 6-ppdQ. And today he'll share his research findings and demonstrate how these analytical approaches are being applied to address real scientific questions. Pete, thank you again for joining us today, and I will hand it over to you.
Well, thank you, Heather and Rogine, for introducing the environmental concerns associated with 6-ppd and 6-ppdQ, and for introducing Pyrolysis-GC mass spec. You provided a good background to discuss some research that my team has been working on. One of the projects that my team has been working on has been investigating developing microfurnace extraction GC mass spec is for analyzing rubber samples for both 6-ppd and 6-ppdQ. So this slide here shows the flexibility of the Frontier microfurnace because our 6-ppd standard came as a solid and our 6-ppdQ came as a liquid solution. So for the 6-ppd standard, we had to grind it so that we got a nice fine homogeneous powder. And for the 6-ppdQ, which was a solution, we came as a solution of 100 micrograms per milliliter in acetonitrile. So we pipetted 25 microliters of the solution into a eco cup, and then we evaporated it. So once we basically have a solid of both, we interject them directly into the pyrolysis unit. So as Rogine has mentioned, the first analysis that we should do is the EGA. So we performed an EGA on the 6-ppd and 6-ppdQ standards, and the thermograms are presented here. The red thermogram is for 6 ppdq, and you see that it has a nice sharp peak starting at around 190 degrees Celsius and ending at around 250 degrees Celsius. For the 6 ppdq, which came as a solution, what you see is a beginning of a tailing, which is actually our evaporation wasn't a perfect, so that was just some of the solvent being evaporated. And then you see a sharp peak starting around 230 degrees Celsius and ending around 290 degrees Celsius. So what we decided is that for our analysis, that what we would do is we would set our pyrolysis temperature at 300 degrees, because then both 6 ppd and 6 ppdq would evolve off at those temperatures. Again, Rosine mentioned it, and I want to reiterate, when we're doing EGA, these are not chromatograms. These are thermograms or thermal profiles, because the column itself it has no stationary phase. So it's just the column is just acting as a lead to go from the pyrolyzer to the mass spec. The other thing that I want to mention is just some terminology. When Rosine had mentioned that you can do thermal desorption and pyrolysis, and I'm going to add a new term so that there's no confusion. When most people talk about thermal desorption, they're talking about having a programmed thermal desorption where the microfurnace starts at a low temperature and you gradually increase. And so essentially what you're using is the thermal desorption profile to separate or evolve at different temperatures, and then using this, you can get a temperature profile, and you can separate out which components are coming out at different temperatures. In Pyrolysis-GC, pyrolysis, you usually set the temperature high enough so that your matrix is actually decomposing. And so what we're going to be doing is we're going to be doing what I'm going to call a single shot thermal extraction. And over here, we're going to set our temperature. In our particular case, we're going to set it at 300 degrees Celsius. And so when the sample goes into the furnace, it's all going to be held at there. And so what we're doing is we're trying to promote the rapid volatilization of all the additives into the rubber. And so the goal here is to maximize the recovery for quantitation market. Again, the whole idea here is that we're trying to maximize the recovery of 6 ppd and 6 ppdq. Here is an example of a single shot thermal extraction of 6 ppd. And so the conditions, we set our pyrolysis conditions at 300 degrees Celsius and and the pressure of 14.5 psi's. And the chromatograms that the column that we used was a ultra alloy +5 column, which is essentially a DB5 column on a deactivated stainless steel support. And so throughout my presentation, I'll be using this stacked chromatogram form. The top is always going to be a TIC, and then the bottom are going to be selected ion chromatograms. And so the first thing is on the top left-hand side, you're looking at a partial mass spec of the 6 ppd. And so what we looked at from the 6 ppd from our analysis is what are the molecular ion and what parent ion and what are the a characteristic ion. So from the mass spec, we decided to trace both 268, the parent ion, and then the characteristic ion 211. And so looking at the chromatograms, you see that there's a single peak at 16.4 minutes. And then when we did a search on the from the full spectrum that obtained at TIC, it came out with a 98% match with the 6-ppd in the standard, which was nice. And then what we're going to do is to do a more complete analysis. What we're going to do is we're going to be looking at the ratio of the molecular ion to the characteristic ion. In this particular case, it's going to be 268 to 211. And so that ratio is 0.462. And when we look at the maximum peak from the selected ion chromatograms, the ratio, the maximum intensity of 268 to 211 was 0.385. And that needs to be commented on is when we look at the maximum intensities of the selected ions relative to the molecular ion and the characteristic ion and a full mass spec, those ratios always tend to be slightly smaller. So we're going to use the value of 0.385 as the as confirmation that we see 6-ppd in samples. And so now the similar analysis we did with the 6-ppd cube. And again, we kept the pyrolyzer at the 300 degrees and the pressure at 14.5. And again, same format. Now, there's a couple things I want to comment on is our library did not have a 6-ppdq standard. So just using literature reported values, our mass spec for 6-ppdq appears to be correct. And so our molecular ion is 298. And then there's the two characteristic peaks that are very prominent, 241 and 242. And so we're selecting the molecular ion ratio to 242. And so in the mass spec, it was the full mass spec, it was 1.31. And then the other comment that I want to make about this is, first of all, you see a couple little peaks coming out earlier in the TIC, and I'm assuming that is just due to the solvent extraction and some remnants from the solvent. And then the other point of interest is the 6-ppdq traces at 298 and at 242. We had to multiply by a factor of 2 so that they could be scaled in a way for us to visualize. And so when we compared the maximum intensities of the 298 trace to the maximum intensity at 290 or 242, we obtained the 1.12. And again, it's slightly less than what we saw in the full spectrum. So what we've shown so far is that we can use single-shot thermal extraction to identify or for both standards 6-ppd and 6-ppdq, and that at 300 degrees Celsius, we're not getting thermal decomposition. But what we haven't shown is whether or not we can use it in real tire samples, and so or real rubber samples. And so in our case, we are going to we went to the local hardware store and purchased some recycled rubber mulch, and we went to our local mechanic and asked him for a used tire. And so we wanted the proof of concept to be straightforward, so we just basically took our rubber and with an X-Acto knife, we cut out a small piece, and then we chop it up into fine pieces and then directly inject them into the pyrolyzer. And the nice thing about this is there's no solvent extraction. It's a quick, easy method for sampling rubber. And so here is the single-shot thermal extraction of the recycled tire mulch. And so the TIC, and so now from now on, I'm going to have their stack chromatograms. It's going to have the TIC and then four selected ions, the 2 for 6 ppd and the 2 for 6 ppdq. So the first thing is this is a real sample. It's not a standard, so it's a lot. There's a lot more peaks involved than we saw in the standard, but there's a clear peak at 16.4 minutes when we collected the spectrum and did a library search. The library search came out as a 6 ppd, and then we look at the ion ratio of the selected ion traces. We obtained a value of 0.393, which again confirmed the presence of 6 ppd. And where the region of the 6 ppdq comes out, the baseline is slightly higher, and there's no clear peak in the TIC. When we look down to the 298 trace and the 242 trace, even blowing it up, scaling it by a factor of 500, we still don't see any clear peaks. So I have an insert that I've expanded the scale so that it's a little easier to see. And I've highlighted the region centered at 18.4, and we're not seeing any clear peaks. There does appear to be a really small peak at 18.7. And then when we look at our characteristic ion ratio of 298 to 242, it comes out at 0.92 and not anywhere close to the 1.12 that we expect. So we're pretty comfortable saying that in our recycled tire mulch, we are not seeing any 6 ppdq. So the question that we wanted to ask here was, is it because the recycled rubber doesn't have any 6 ppdq, or is somehow what's happening is that we're getting some thermal breakdown of the 6 ppdq in the tire matrix that we didn't get in our standard. So we spiked the 6 ppd. We spiked the recycled rubber mulch sample with 6 ppdq, 25 microliters of 6 ppdq, and evaporated the solvent, and then did the thermal shots, thermal extraction. And so what we see again is a sharp peak at 16.4 minutes. And this time now we definitely see our 6 ppdq sample coming out at 18.6 as expected. And the ratio, you see the selected ion ratios of 3.77 and 1.06. So we're confident, and we have now ways to confirm the presence of both 6 ppd and 6 ppdq in rubber samples. But what we haven't shown is whether we can actually detect them in a native rubber samples. So over here, this is a tire, an automobile tire tread that we obtained from a local mechanic. And again, we did our single shot thermal extraction. And for, again, looking at the TIC, not unexpectedly, the TIC is much more complex even than the recycled tire mulch. But we still have a very sharp peak at 16.4 minutes. And looking at the mass ratio 1668 and 211, we confirm that that is a peak associated with 6 ppdq. 6 ppd. And then we looking at the region where the 6 ppdq, and now the noise, our baseline noise is significantly higher, and it's very hard to tell whether there are small peaks hidden in the noise. But looking at the ion chromatograms, blowing it up in our insert over here, we see that there's two peaks in the region of interest, one that comes out at 18.6 and the other that comes out at 18.7. The peak that has at 18.6 has a ratio, characteristic ion ratio of 1.26, and the peak that comes out at 8.7 has a characteristic ratio of 0.79. So again, we're able to distinguish. I think we can confidently say that we detected 6 ppdq in a true tire rubber sample, and we can distinguish it from an interfering ion that comes, or interfering compound that comes out at 18.7. So to sort of summarize what we have so far is that we have that we can use single-shot thermal extraction of rubber to directly detect 6 ppd and 6 ppd Q and rubber with minimal sample preparation. But selected ion monitoring using retention time and ion ratios we can use to confirm the presence, that we can distinguish the difference between 6 ppd Q and nearby interferences. And I think the point here is that you can use single-shot thermal extraction as a quick method for screening rubbers. So the next point that we really want to ask is, can this be quantitative? And so to do that, we have to actually address a couple issues. The first issue is, and they're both actually associated with, that pyrolysis is a very sensitive technique in that you really only need sub-milligram amounts of samples. The first question is, if you only need, 0.2 milligrams of the sample, how do you get a representative sample of your tire? And then the second is, how do you accurately measure the small amounts? Trying to cut with a little piece with your knife is not going to be at a reproducible method. So what we did is we cryo-milled the tire tread samples that we had, and to ensure that we had representative samples, we collected 30 grams of the tire, and we randomly selected pieces across the whole tire, and then when we cryo-mill, we get very small particles, and the small particles then is more homogeneous sample mixture, and allows us the small particles also allows it easier to be measured on a microbalance. So we addressed the sampling issues, and so now once we address the sampling issues, what we're going to do is we're going to use standard addition methods. We took the 6 ppd and dissolved it in toluene, and then the 6 ppdq was already a solution. We added both to our rubber, the cryo-grilled tire tread, and we were able to do some standardization. Before we did this, what we wanted to do, though, is we want to collect an EGA of the cryo-milled tire tread to make sure that the cryo-milling did not somehow affect the rubber components. So we ran the EGA, and very similar to the EGA that Rogine showed, the additives and volatiles come out before 320 degrees Celsius. And then above that temperature, we're getting the thermal decomposition of the tire itself. And so what we're going to do is, instead of the 300 degrees Celsius, we're going to use 320 degrees Celsius to make sure that we get all of the additives out of the sample. So when we did our quantitation, we were able to obtain nice linear graphs with R squared of 0.999 for both the 6-ppd and 6-ppdq. And in our tire sample, we found that we obtained 525 nanograms of 6-ppd in a 204 microgram sample. And so that comes to that the amount of 6-ppd that we obtained using thermal extraction was 2.6 milligrams of 6-ppd per gram of tire, or approximately 0.26 weight percent. And for the 6-ppdq, we obtained 152 nanograms of the 6-ppdq in the 204 microgram sample, which converts to 0.75 milligrams of 6-ppdq in a gram sample of tire tread, or 0.075 weight percent. So how does this compare with other literature values? And so I made a table here of the highest values that we saw. And the highest values that I see using a solvent extraction LC-MS-MS method came from Foyer et al., and they reported a value of 2.7 milligrams of 6-ppd to 1 gram of tire tread. But their 6-ppdq that they obtained was much lower, 0.030 milligrams of 6-ppdq. For the thermal extraction, Regine presented the thermal extraction work of Frost et al., and they obtained 1.2 milligrams per gram. And to just sort of contextualize it a little bit more, the amount of 6-ppd that rubber manufacturers put in tires is somewhere between 0.5 to 2%. So the fact that we're getting a value of 0.26 weight percent tells us that we're getting a pretty good extraction of the 6-ppd. Very quickly, I'm just going to comment that if we're going to use this for a screening method or a quantitation method, that what you need to do is really have a auto sampler. And we're fortunate enough to have the Frontier Auto Shot Sampler, which allows us to basically allow the analysis to rerun unattended, and allows us to have a higher throughput, and is easier and more representative for quantitation. So in summary, what we using the single shot thermal extraction, it allows us to have a direct method for without having to do a solvent analysis. We using the SIM and retention time values, we can confirm the presence of both 6-ppd and 6-ppdq. That getting the cryo-milled tires tread allows us to get representative tire samples, and that the quantitative work that we showed is, first, yes, it is quantitative, and two, it is comparable with the best in both values in both 6-ppd and 6-ppdq. And in fact, actually, it's 25 times higher than any reported literature. I'm a professor, so most likely I didn't do the work, and that's exactly right. I had 3 students who worked on it. Gabe Ferrante started the work. Heidi came in after and did a lot of the detailed work, and then she has since left, and we have Austin Riley, who is actually a technician in our lab, completing the work. So really, they're the ones who really did the work. I'm the one here standing up. Now, we have a great relationship with both Shimadzu and Frontier, and through the Spark grant, we are able to acquire a lot. We are able to acquire instruments for us to do the work. And Frontier has been allowing us to use their pyrolyzers for almost 4 years. And so we thank them very, very much. Lastly, we don't have a microbalance in our lab yet. And so we borrowed the microbalance from John Carroll. And so we need to thank Michael Nichols, and Mike Sutter is in our lab, who acts as an advisor and was the one who advised us to go to Mike Nichols. So lastly, here are the references to the rubber that I talked about. So thank you very much for your time. And it's time for me to ask Chris to bring us back to the question and answer period.
Awesome. Thank you so much, Pete. No, that was great. I love the acknowledgments. Definitely a team effort and lots of great information. And I was telling the team beforehand, I know what people read on rubbernews.com and looking at our data, and I can tell you that this type of research in 6-PPD is at the top of the list. So very interesting to the audience for sure. We have a limited time for Q&A. Lots of good questions came in during the webinar. If you have something else you'd like to submit to the team, you can use that Q&A box on the screen and send it our way. And we'll send out some follow-up information so you can get in touch with everybody if we can't get to your questions. So I'm going to dive right in. And Dr. Tandler, I think this first one is for you. The rubber is tire rubber is a complex chemical and challenging matrix. Do you have concerns about interference or consistency?
Well, I think there's a couple things. I think cryomilling addressed some of the consistency because the tires are probably not homogeneous. So you really do need to collect a fairly large amount of the tire in trying to grind them and getting a uniform part. That addresses some of the consistency. But by using the internal standard or the method of standard addition, we addressed the issues associated with whether or not an external standard would work and if there's any matrix effects.
Okay, great. I think this stays with you. How do you extract the parent and characteristic peaks? Are you performing a sim analysis or are you using a functionality of the software?
No, so we're actually performing a full scan and then a series of second SIMS analysis. So all of those are individual SIMS. They're not extracted from the full scan. And that allows us to get greater sensitivity. So what I didn't show you are all the negative results. So if I look up, if we look in the region of 18.6 where the 6-PPD-Q shows, you're barely going to see the ions for 6-PPD. But by using SIMS, you collect a little bit more information, and so but I failed to comment. The 6-PPD-Q traces that we're seeing are usually multiplied by 250 times, 500 times. So they're small signals, and so you have to do SIMS.
I think we've got time for maybe one more, maybe two more. We'll go a little over. Appreciate everyone staying with us. Here's one. Is it possible to use the Shimadzu PolyArc FID for quantification instead of the standard calibration? Oh,
sorry, Mark, I would hand it over to you.
There you go, Mark. Yeah.
Yeah, sorry, I was muted while I was talking. All right. So for those that don't know, the PolyArc is a Shimadzu detector that converts organic compounds to methane for a universal signal response. So one thing with using that is you will lose your qualitative information and selectivity since you won't have the mass spec if you're not using mass spec to get the ions. So you can't do a library search or ion confirmation. Now, whether you can use it for quantification, maybe. I don't know of anyone specifically doing it. but it may be possible. It could, warrant some further investigation using that.
I always love that when the question comes up, and a lot of times it's like, hey, let's follow up and talk a little bit more about that. There may be something there. I've got time for one more. Let's go with this one from the audience. How did you settle on cryomill for the sample preparation? Were any other techniques considered?
Well, I think I first of all, I used some literature search, and I think there's a lot of literature using cryomilled rubber samples, and I think that's just a standard method in the rubber industry. I also have some just years of practice of trying to mill stuff, and I know that whenever you're trying to mill polymers, lots of times you end up getting sticky globs if they're not cold enough.
Okay,
So
great.
A little practical experience and a little literature.
Okay, that's fair. Totally fair. I think that's pretty much all the time we have for today, but I want to take a quick second to thank everybody. Heather, Rogine, Dr. Tandler, Mark, walking us through all this. It was terrific. It's a good practical look at a method that matters more and more. And I really appreciate you taking the time to share your expertise with us. For everybody in the audience, you'll get a follow-up email with a link to the webinar on rubbernews.com in case you want to share it with some colleagues or rewatch it yourself, as well as follow-up information to get in touch with anybody here. So again, I want to thank you for your engagement. There were a lot of questions we couldn't get to, so hopefully everyone can follow up, and appreciate your time, everyone. Have a great day.